So then, oops, already the first mistake. Now welcome to this first lecture in computer algebra systems in summer term 2025. So this will be the only lecture in this course where I do something PowerPoint-ish. Yeah, and the PowerPoint slides, I have to apologize here. So you will notice that I'm doing this kind of lecture for some time. So they are not the newest PowerPoints, but I did not change them because most of the stuff is, did not really change. Yeah. So the thing that you have to also understand. Nowadays, maybe the youth doesn't have this problem nowadays, but actually now many of these concepts that we learn in computer stuff, even including artificial intelligence, yeah, they have been around for quite a few decades now, yeah? And this is also true for computer algebra. Okay, some also you'll potentially notice that these are not necessarily the newest versions of the programs. Okay, first, what actually is computer algebra? So often when I ask in this kind of lectures whether people have already used some computer algebra tools, then I often get the answer, yeah, I used MATLAB. And even though there are some add-ons to MATLAB that you can do computer algebra with, MATLAB is of course not a computer algebra system, not an intrinsic computer algebra system. Computer algebra system is a system that does algebra, yeah, so manipulation of structures, mathematical structures. Yeah, we'll come to this. And and they have been around since the 80s, and actually. One of the first one is also the one that we'll potentially exclusively we'll see use in this lecture. This is Mathematica. So Mathematica was not the first computer algebra system because this person who introduced Mathematica, Stephen Wolfram, he had a different computer algebra system before that, yeah. So and so with Mathematica, this, you know how these people are, we invented the perfect thing, and this is now around for more than 30 years, yeah. There is, okay, so this is a commercial tool, and by the way, for a very, very long time, computer algebra system was, you could say, exclusively commercial. Yeah. So the other big commercial tool is Maple. Of course, this is coming from Canada, so maple leaf. Yeah. And this. You'll notice that they are in competition, yeah, with Mathematica, yeah, and we'll see in a moment how this is actually expressed. So as we professors like to say, when I was your age, I had this thing here, TE. 89. I think you can even buy these things today. They haven't changed a lot. And this was a mobile computer algebra. I actually have. I had one. I still have this, and it's still working. Yeah, and it's built in 1999. And I mean, it does computer algebra, yeah, and I mean, it's slow, obviously, but it does the job. So one prominent thing that is missing, and maybe because I use here these old slides, is now SymPy. Yeah. So SymPy is one of these libraries in Python that you can load and that implements a computer algebra system. And this is more or less, I mean, okay, maybe I'm lying here, but this is the free stuff compared to this commercial stuff. Talking about this commercial stuff, you should also say, okay, so what does commercial mean? These I mean, for a very long time, maybe this has changed a little bit, but for a very long time, these tools were exclusively used by scientists and engineers, yeah, and in particular engineers also in industry, yeah, like we do the software for the for the aircraft engineers, something like this. So they this means these software are not cheap. Yeah. So I remember when I learned this like 25 years ago. Yeah. I told you how old it is. The student version for Mathematica that would last until the end of the year, not a year, but when you bought it to the end of the year, yeah, it was 450 Deutschmarks already, yeah. So and then now we switched this here to summer semester, which is a good thing because previously we always had this in winter semester. So if you have it in winter semester, you have buy the license twice. Yeah. Okay. I mean, of course, they would assume that you use it for the rest of your life. But I mean, a student version of Mathematica 450 Deutschmarks. I mean, like you could say you cut it by half, but then we had a lot of inflation in the last 25 years also. Okay, so SymPy, yes, SymPy is missing here. But SymPy, since it is an add-on on Python, it obviously is not a native computer algebra system. Yeah? So you have to declare things as algebraic type, and then you can do manipulations on that. Okay, I'm not very familiar with SymPy, maybe because I'm an old guy and I've been growing up with Maple and Mathematica, with these old things. And I mean they are still sold. That there's a free tool does not necessarily mean that these things are obsolete. Yeah. Actually, recently when we had some comparison, the Mathematica did produce the better results than SymPy, but maybe that was, I don't know, could just be coincidence or not. Well used. So okay, I give you very short view on a Maple session. I have to admit, so this is like Maple from 15 or so years ago. We don't have a Maple license. So I cannot reproduce these things. This is why I'm using old slides. Yeah. So you can just to give you an overview, you can you for example you can define this variable c. Yeah. So you define this by dots equal colon equal, and then you type, and while you are typing, Maple will. So the old Maple at least and the new Maple certainly too, will interpret your writing and will automatically put this into this, what we call pretty printing format, right? And then after you typed it and executed it, there's actually a small, transformation of this. You already see that this is a transformation of this here, because it's here, this is 2a plus 6 divided by 2a, and here it's 1/2 times 2a plus 6 divided by a. So it already, you just entered something and it already did a algebraic transformation on that. Yeah? So now this is different. This is now a different thing from how you would usually store things. Now there's a variable a in this. You can set this a to 3, and then you can evaluate c, and then you get 2. And now in the traditional programming languages, you would assume that now 2 is stored in the variable c, right? But this is not the case. So there's the algebraic structure. This algebraic structure is stored in c, and this only evaluates to 2. So if later you change a, c will evaluate to something else. Yeah? So this is the difference from you do things in the other programming languages where we are not using algebraic types. Yeah? So of course you can define algebraic types in programming language as there is doing in SymPy, but the intrinsic types will not, in other programming languages, will not behave that way. So then let's okay, so what we do today is a little bit different from what we are going to do the other lectures. But first, this time we try to understand how this is internally implemented. With the problem is, like all of this is commercial software, we don't precisely know how it is implemented. Yeah? But how, in general, computer algebra systems are implemented. So there would be, algebraic types, they don't have, constant space in memory, right? So if you have an integer, double or floating point number or something, you will always know a priori how large this thing is, and you will allocate that memory for this, and then you can put something in here. Algebraic structures can be arbitrary. Yeah? So this means that there needs to be some some graph structure, like a tree or something more complicated than a tree, yeah, would have to be implemented in this. And now this is how you can imagine this. So I distinguish here between an atom. So an atom is in the classical Greek sense something that can no longer be split apart. So this is the end of the the end of the tree, like a leaf. So this is actually something that can no longer be taken apart, like the the usual things that we have in programming language. So this would be, for example, an integer, or it would be a floating point number, or it would be an actually what is it called? It could also be a vector if you like. Yeah, but no, it would, because a vector you can split up again. No, it can also be a non-rational number like pi. Yeah, for example. Yeah. So So then I'll get here that there's a declaration so that we can actually define something, and then we need headers and links. So we need a header to say what type of thing are we talking about, and we need the links to actually build our tree that is then our structure. And now let's look at this at this session here. So we'll have a declaration. So we define something. We define our C and we define our A. Yeah. So the A is pretty simple. So we put an atom into the A. Yeah. But the C is a structure that we have to split up. So the thing that we put in here is you could see this is like the operator is the header. Yeah. So we have here 2a plus 6. Divides. Okay. No. It's not that one. Sorry. Okay. I was looking at this one, but we are already here. Yeah, we are already here. Yeah. Do you see my cursor? Yeah. Okay. See, this is. So the outermost part here is this multiplication of this 1/2 and the rest here. So this is times, yeah. So times is a binary operator, yeah. Okay, in Mathematica a little bit more complicated, but in general you could think one thing times another thing. So it has two arguments, yeah. So and in each of them we put a link, yeah. So because the thing here is it's too complicated. This again we have to split it up again, right? So here in the first we set a divide, and divide again has two things, namely 1 and 2, and these are now again atoms, and they will be in the computer algebra. They will also be stored like this. So the computer algebra will not say the 1 divided by 2 is 0.5. This is not what a computer algebra system would do. Yeah, because this is these are integers, and 0.5 is a fraction. So it would, from the perspective of the computer algebra system, it would change the type. Now, you could say that in that particular case, 0.5 is, you could say this is exact, yeah? But say you have 1 divided by 3, then there is no exact representation of these. This is why this is not split up. So we'll distinguish between integers and fractions. So when you put a point or not a point behind the number, yeah? So, I mean, if we want, for example, can always have here our Mathematica. I'll go down here, make this a little bit larger, yeah? So 1 divided by 2, yeah? So is 1 divided by 2. Now you can force this by putting a 1 point, yeah? So then you will imply that this is a floating point number, and then it will also execute this like this. So this is how computer algebra systems would behave. Clear? Okay. So let me. Okay. So the other here we've divide another link, and then basically at the end we come to our atom. So the atom can also be a variable. Yeah. Then it's so this variable here is again an atom. Actually, if you define something that you can split up, yeah, this could also be changing. Okay, I didn't want to talk about this now. Yes, so obviously the algebra system has to know the algebraic rules, yeah, and I mean they are is something that you know if you get them into your body somehow you potentially forget that they exist, yeah, but for the computer you always have to give the rules. So for example, commutativity, yeah, so the computer algebra system has to know that for example for times and plus these operations it has to be able to exchange the order. Then it would know identity. So for example, we know identity 1 times b is b and 0 times b is 0 plus b is b, right? So I mean 1 times b, d, no, d is not a good b, yeah? So let me see, is b, yeah? So it knows automatically this this identity. So when I go here, it's always yes, and then there may be exact operations. So for example, if you divide 4 by 2, if you divide 4 by 3, it will keep it 4 by 3, right? But if you divide 4 by 2, then this is 2. This can be exactly done. So this will usually be executed. Okay, so these rules are implemented, and it's up to the decision of the programmer there what heuristic they use, in which order they will manipulate this. So this is the part because there is no, I mean, if you do algebra, there is no exact way how you should proceed to simplify, for example, something. So this is the art in this, and this is also where the result of, say, of Mathematica and SymPy may differ. Yeah. So I can't tell you what really is doing all the time the better job. The Mathematica guys do this for 40 years. The SymPy guys do this for 5 or 6, maybe 10 years, I don't know. So they will be different. Yeah. Actually, the simplification, yeah, we'll come to this, I guess, is the thing that's difficult to implement in this, and where you also may sometimes be disappointed. Okay, now let's see some of these manipulations here potentially in action. So you'll have AB plus C is AB plus C. So these transformations go both directions. So it can take this and transform this to this, and then it may see whether it can do something else. So it's not intrinsically clear whether you want to store this here or that here. Yeah, yeah. As you do algebra on your sheet of paper, you may, you may change this and may change this back because you see, okay, it didn't help me. Yeah. Yes. So A times B by C can be expressed as A B C, and divisions can be split up too. For example, that could make sense if there's an exact operation when you find, okay, there could be an exact operation here in between somewhere. Okay, so now you could then see that you by transformation you can make algebraic simplifications. So actually, I think Maple didn't initially do a very good job by splitting this up, because as you see, if you look at this as a human being, so there's 2a plus 6, so you can divide this by 2, right? So Now, what the algebra system has to do is has to do some transformation. For example, putting this 1/2 inside the division. Yeah, 1/2 times 2a plus 6 divided by a. And then we will have the distribution law where because there's this bracket, so we distribute this 1/2 to all of them. And you see 1/2 times 2. Here I actually have to do another. Did I have this? So another transformation. Yeah, so that 1/2 times 2 is 2 times. So now, I mean, it's dangerous because you could also say it's 2a divided by 2, and then you have to split up again. So so if you see as a human being, you should take the numbers out only. Yeah, maybe there's some heuristic in this. Okay, keep the numbers out and see whether we can make some simplifications just with the numbers. So then we have 2 by 2, and 2 by 2 we can calculate and get to 1. Yeah, and then we have to use the identity that 1 times a is a, and then we come up with this, and then you could still say this is 1 plus 3 by a if you think that the more interesting way to write the result. But all of these things are equivalent. Yeah, and usually we consider something simpler if the entire tree is smaller. Yeah. I mean, what does it mean something is, so there's an infinite way of expressing 0, for example, right? Yeah?
So what a question here. So maybe the system, what it's doing is it starts with something and starts splitting, and then when it has a smaller, when the result cannot be longer treated.
No, so usually I don't know whether we come to this. Okay, maybe we'll also come to this in here. So, okay, what I come to this question in 2 minutes. Yeah, so just a small comparison with this. With these two tools. So Maple and Mathematica use this concept. I mean, I think this concept actually is invented. I don't really know, but I believe the notebook concept is invented through Mathematica. I mean, was there? I don't know any earlier occasion of this. So nowadays, people use Jupyter notebooks or Pluto notebooks, yeah, where they are familiar with this scripting thing where you have small boxes where you execute a thing. So in previous generations, as you see, I do this for a lifetime already. You had to explain this in more detail to the students because this was kind of new. But this comes from computer algebra originally. Yeah. So you have an input, yeah, where you type something, and for example, here in Maple will already manipulate stuff while you are writing this. Mathematica is the old-fashioned thing where it keeps what you type the way you type it. Mathematica, we'll see this later, allows different ways of inputting, yeah, but it's also compatible to the stuff that they had in the 30-something years ago, because the software is 30-something years old, right? And there you would, so you can type there everything in normal text, yeah. So without any additional objects or square root things. So you can write everything in text, but you can also write everything graphically. Yeah? So, but say you type everything in text here, and this will already manipulate this Maple, then there will be the output, and the output is already put into a pretty state. So this is what we call pretty printer, so that you can read it the way you would read an equation. So, and then as the input, now I'm coming to your point, or to your question. So there is, I mean, if you look at this in detail, then Maple actually did a little bit of transformation to this. Yeah, so this is not actually exactly the same. It did more of a transformation to this than Mathematica, but Mathematica also did a transformation to this. Yeah, so this is also not the same, because I wrote 2a plus 6, and this is not the same. It's 6 plus 2a. So what Mathematica actually does, which I say so from empirical observation, it is ordering stuff alphabetically. Whatever point they have behind this. I mean, like if you use this for deriving, so I mean, computer algebra is used for now many decades and to generate computer code that you then use in further, tools. So to write, you use computer algebra to write code. Yeah. So this was before ChatGPT. Now everybody does this, but computer algebra is in computer, I mean, you just get the equations out, not the entire, control structure usually. Yeah. So then it's important how this may order stuff. Yeah. And it seems to order this in an alphabetic ordering, apparently. So, however, it will not automatically try to make this thing much simpler, unless there is something very, very obvious. Like you divide 4 by 2, then it will simplify this. Yeah? But other than there is something very, very, very simple. So you see, for example, they did not try to divide by 2. So you as a human being seeing this, you would potentially write just 3 plus a divided by a. Yeah, but the Mathematica, so the computer algebra system will usually not do this. That's already too complicated to do this without you asking it to do it. Now you can ask computer algebra systems, most of them, to do this simplification, and this is done by calling the function simplify that exists both in Mathematica and in Maple. And there is a difference in nomenclature. So, for example, in Maple you write this with lowercase, and in Mathematica you write this in an uppercase, and you may ask, so what does this? So what? It's just a little bit different, but actually there's a meaning behind this, because in Maple you can write the function with uppercase and with lowercase, and they behave in a different way. Yeah. So when you write simplify in lowercase, you tell Maple that it should evaluate this function. Yeah, we come to this in a moment. Yeah, so you basically tell them do this now. Whereas when you write it with a capital, then yeah, do it, but later. Okay. So there's the concept of eager evaluation and lazy evaluation. to which we come in a moment. So eager and lazy evaluation is an important concept of functional programming. And functional programming and computer algebra are very closely related things. Yeah? So, because actually in computer algebra it makes sense that you do functional programming. So in functional programming, you can always distinguish between, you know, I define a function, so something that should do something, but I don't want you to do it now. Yeah, I only want you to do it when I give you, you know, the data for doing this. Or I want you to do it now. So I have to distinguish between these two things. So computer algebra usually gives you the opportunities to distinguish between eager evaluation and lazy evaluation, and these two things behave in a different way in Maple and in Mathematica. If you ever want to, I mean, I don't want to discourage you from using Maple. It's just we don't have a license, so I cannot show you. Okay, so yes, so maybe I'm not sure that this may be similar now to how it's done in was it the Jupyter notebooks, but I'm not very familiar with these Jupyter notebooks myself. So in Mathematica you have these cells, yeah, that you can execute in arbitrary order by going there. So you'll go there. Let me see. Why am I not? Okay, so you see, here are cells, yeah? So they are not in any particular order. Yeah, I can go there and execute them. So if these cells can of course be of different size. So so it doesn't like this, so I'll do a semicolon. And I can, for example, write, I don't know where it's read. Say, okay, I'm doing something stupid here, yeah? So I do two operations. I can also put two operations in the same cell, so you can see it does a very simple transformation of this 5 plus z. Yeah. Let me see whether I was lying to you. A, B, C, G. Yeah, it's alphabetical for whatever reason. Okay, so the way you execute this is to distinguish between enter and return. Yeah? Which I guess because people are now using Python, they know what this means. Yeah? So I mean, if you have a laptop, then you don't have an enter, you only have return. So carriage return puts you on the next line. Yeah? So I come here in the next line when I go press return, and if you will, enter is the uppercase return. So you use shift return or enter, yeah, to execute the cell. Okay, so this is the one basic thing that you have to know to get actually started with this. Okay. You can also go to the menu and ask to execute everything. Okay, I guess that's simple stuff. Now let's talk a little bit of what you can do. Yeah. So this lecture will of course be mostly on solving differential equations with Mathematica. So let's see what we would do. For example, if we have an ordinary differential equation that we would like to solve. So we have a computer algebra system, so we can do a few funny things. So we can put in an equation, we can declare a variable ODE as this equation. Yeah, and see this equal. So this two equal signs. This is the equal sign of used in the equation. So the other one is a declaration or assignment. And I was already talking about eager and lazy stuff. This here, which will have to distinguish from the others, this is an eager declaration. So whatever you see here, execute this and put it into this here. Yeah. So it's important. We come to this, but it's important to understand the difference between eager assignment and lazy assignment. This is an eager assignment. And this here, by the way, the equal sign, there's also a lazy and an eager equal sign. And if you want to write an equation, you always use the lazy equal sign, because otherwise it would try to execute, to evaluate whether this is now equal. Yeah? So this thing here, I mean, if we come to the exam, I will ask these kind of questions. So is this operation lazy or equal? Yeah? And putting an equal sign here, this is also considered an operation. Yeah, this is a function. It's implemented as a function, and this function is a lazy function. So each of them is either lazy or eager. Yeah. So, and this is eager. So now you put. You can write these funny Greek letters. You can also write Chinese letters if you like. Yeah, they're maybe a little bit more complicated, but. Okay, we'll come to how we write them. It's not important now. And so you can put this in. And what you can also do is you can write this D. So this D is an uppercase. This means it's a built-in function. And this D is the differential, which again you can write in different ways. So for example, you see, I write this differential D of x of t. So x is a function of t. Yeah, I tell them that x is a function of t. Otherwise, this doesn't work. And then I say this is t and t, which is one of the 25 ways you can tell Mathematica that it takes the second derivative of x. Yeah. So and you see, it's already. It does not write it down, so the pretty printer writes it in a different format. Yeah, so it does it with these two. So you can also type this. If you type this, you always have to take care, because there are so many. There are three different kinds of, these upper ticks. So you have to pick the right one, otherwise it will interpret this in the wrong way. That's a pretty annoying. I mean, actually, that's pretty annoying, because you don't necessarily see this. So if I type it like this, yeah. So let me see. I'm doing something stupid now. Actually, I have to tell you that I don't know myself. So say I'm putting this. You see, this is not the same thing, yeah, because I used the wrong apostrophe, yeah. So which one is the one that I have to use? this actually looks wrong, but is right. I find this extremely annoying. Yeah? Okay. But this is the way it is. So, okay, now we have defined this partial differential equation, and now we can, this ordinary differential equation, and now we can use built-in functions to solve. I mean, this is what function is this? This is obviously a damped harmonic oscillator, right? Yeah. So now you can take this ordinary differential equation and tell Mathematica to solve this as a differential equation. This is why it's called desolve. So this is for solving differential equations. Don't use this for solving algebraic equations. For solving algebraic equations, we have solve, yeah, obviously. Okay, so this thing doesn't has a unique, harmonic oscillator doesn't has a unique solution. So you have to specify these parameters. Otherwise, it doesn't know whether you are in overdamped, underdamped, or configuration. So this is now an underdamped configuration. And what we do now here is we do a substitution of the parameters in the equation. Yeah. And again, there are different ways of doing this. So if you think too much in the way you would think from a usual programming, standard programming way, you would put, one thing that you can do is you can define this variable zeta and omega to be 1/2 and 1, right? So then what you have done is you have put values in this variable, so you have overwritten them. Yeah, so they will have this value for the entire future. But this is not what you want. What you want is now assume for this particular case that it has this value. Yeah? And for this you use a substitution. So you don't put, I can write a new line and say zeta equals 1/2, okay? And then it will behave, the rest of the program will behave like zeta is 1/2, yeah? Until I change it again, yeah? But here I want to say, assume here, only here, that zeta is 1/2. So, and this is done by, actually this is supposed to be the introduction of a lambda function, if you're familiar with functional programming, but I would rather recommend to see this in a little bit a different way. So if you write down equations on paper, yeah. So maybe I'm misusing my other slide here. Was already okay. I forget what is on the what is on this book here. Yeah, just say you will have, for example, you'll write a differential dx, which is a function of t divided by not divided. So say you take this differential, yeah, and then you can write that t equals to 4 or something, yeah, maybe 4 seconds, I don't know, right? So the way you should understand this this dash here is, you have an equation, you write this line, and then you write the replacement rules here, right? So this is basically what you also do here. So you write this. It's actually, so this is not a division, yeah. So this is the operator is this slash and the dot, yeah, slash dot, and now you give a list of these replacement rules where you do the substitution. So they will be substituted into this ordinary differential equation here, and then you tell the dsolve what is the dependent variable. You give a list of dependent variables, so there could be more equations, right? So you give a list of dependent variables and a list of independent variables. Yeah, so the independent is here x of t, and because it's a computer and a computer is stupid, you have to tell it that x is a function of t. So it's not enough to say x is the dependent variable. You have to say x as function of t. Yeah? So now you get these results with some constants, and you also get a list of solutions. So the reason why there's two lists is there could be different solutions, and this, if you have, if you solve for more than two equations, and you may have different solutions, then one solution for x would correspond to one solution with y, and the second would correspond to one solution, the other solution for x would correspond to another solution for y. So this is why you get lists of lists here. So now you can do this obviously in a different fashion. So also for the overdumped. And what in addition you can do, so you get a different result obviously, and what in addition you can do is you can also set here initial conditions. So this case here has constants in it because we don't have initial conditions. So when you give instead of just the ordinary differential equations, you also give equations for the initial conditions. You can already determine this constant so that the solution will come out without constants. Yeah? So the way we give here the initial condition is, for example, saying that x of 0 is equal to 1. Yeah? And so, we have a second order differential equation. We need 2. So we'll set the value itself to 1, and then we also want to set the derivative in the beginning, first derivative, to 0. Now, if we use, if we have this problem with writing the right apostrophe here, yeah, then we are a little bit, you should just use the right apostrophe and then there's no problem. But let's see you are troubled with the German keyboard, yeah, or whatever, yeah. Then you can do it this way. So what you cannot do is to write x of 0 a derivative of t. Yeah, because this would, you can write this, but what obviously will be the result if you use, dx of 0, because this is where you want to evaluate, yeah? And you will take the derivative in t. So what happens? It's 0. Because x of 0 does not depend on t. Yeah? This is a computer. It's stupid. Yeah? So don't think it's thinking for you. Yeah? Maybe all of this will change when they build in ChatGPT. Unfortunately, Stephen Wolfram is a big fan of ChatGPT, so we'll see very soon Mathematica being completely intertwined with a large language model somehow. Yeah, so we actually have to tell it that we mean by t, and once we have done this, then we can replace t by 0. Yeah? Okay, going back. So we say, okay, this is, we set up this equation and then we replace. So now take care, this is only acting on this one here, yeah? This is only, this t will be replaced only here. And here we replace this constants, and then we solve, and then we get the equation. Then we get the result without constants. Okay. So this is something that we are going to use a lot. Solving differential equations. Now, yes, this I told you that there is this replace all thing, yeah, that goes with the slash and the dot. So we have x by the power of 2 is now replaced by x equal to 2. Is rule replace x by 2. And one thing that, one question, of course, is how do you actually make this error? Yeah, I just lazily typed it a minute ago, right? So what I did is I write minus, and the what is this, the larger sign, and I get this error, yeah. But this is, if you don't find this, there is something you call syntactic sugar, sweetener, yeah, artificial sweeteners. So all of these functions can be written in different ways. So there's always shorthand, yeah. So I can, this arrow is just a shorthand for rule T0, right? And another this slash dot is also just a shorthand. So you can, for replace all, for the function replace all, yeah. And actually this applies to everything as stupid as you can think, yeah. So it's plus 3 and 7, yeah. So everything is implemented like this, yeah. So this here, by the way, also this operation here is eager. If you put this arrow, you get an eager rule. So now this is one place where you actually get a pretty large difference between eager and lazy things. Yeah. So see, you can have, now we can also write a lazy. So usually there's, when you have one operation that is eager, then you'll have another one that is lazy. Yeah. So you can distinguish between the eager and the lazy. The lazy one. So what happens now? You can see the difference. What is happening with an eager replacement and an eager rule and a lazy rule. So say we have 3 occurrences of x, and then we replace x by a random number. Then when you are when you tell Mathematica to be eager, then what it's doing is it will execute. So it sees it should replace x, so it's executing this and see what is x. And then it will put x everywhere where it belongs. Which, because it executed it once, it will give all the same. Yeah? So this means you put something on the desk, it will automatically do it. Yeah? So, and the lazy thing is, okay, I put something on your desk, but you say, okay, hold on, see whether you need it. Yeah? So now when it meets an X up front here, then it says, okay, now I have to do this. Now I evaluate and put this inside. Yeah? And then when it encounters another X, it will do the same thing again. Yeah? So you see, this is not necessarily, I mean, often using eager and lazy evaluation has something to do with efficiency, but it can also mean doing something entirely different. Yeah? So yes, compute then replace, and replace then compute. These are the differences.
Sorry.
Yes.
The syntax is these two dots and criteria.
Yes. So this is right. This is the lazy rule. Okay. Okay, so then there is another thing that we have to use a lot. This is it's a little bit different from lazy and eager, but also has similarities. We can do a replace all. This is the slash dot. Yeah. This will replace all occurrences of the thing here in front by what happens later, but it will do it only once. And if you have, for example, what is it called? Recursive, yeah, recursive function. Then like for example the Fibonacci sequence, yeah. So then it will just give you the next iteration of the Fibonacci sequence, yeah. So now what I'm doing here, we'll come to this what this means here in a minute, but we replace this f by a function f of x, where we replace again x, yeah, with these things in an if statement. So if statement condition true, false, and actually there is, because it's computer algebra, Mathematica also allows you to give you, instead of true, false, and undecidable. So you can have an undecidable result. Yeah, so if it does not know whether it's true or false, it can give another one. But there's also an overloading. We come to overloading in a minute. So overloading means that when the signature changes, yeah, you will different implementations for different signatures. So for example, you don't need to give an else part. Yeah. So if you just leave this comma out, then it will also execute correctly, but will not have an else. Yeah? Okay. So if you want to repeat this, because f is a function of f, yeah? So what you can do is you can this replace repeated, which is just two slashes. Then what it's going to do is it's doing the substitution in the expression that you presented, and then after doing this, it will take the same substitution and will take it again into this expression until it does no longer find anything. It has nothing more to substitute, right? So now what it will do here when you execute this with 6, yeah, it will do it with 4 and with 5, and because we have this clause that when x equals to, so this will only be executed here So this will only be repeated as long as x is larger than 1, and because we are getting smaller, yeah, it will finally get to 0, and then this will terminate, and then you get 8 out of the sequence. Yeah? Okay. So this will recursively apply the rule. Now we still have to talk about the patterns, which are at first occurrence maybe patterns may at first occurrence be difficult to grasp, and they are actually pretty complex, but we do the simplest case here. So you may be forgiven to think that you can define a function like this. Yeah, g of x. So this here, by the way, is a lazy assignment. So it will not try to execute this immediately. So you do a lazy assignment and say this is 2x. Now, if you put as input g of 3, then it will output g of 3, because you defined that this is g of x. And you did not indicate that this would be true for anything else than x. Right? So it will only take g of x as being 2x. So when you want it to understand this x as being something algebraically replaceable, then you have to use a pattern. You have to say that this x is something that can be substituted with something. Yeah? Even in the function header you have to do this. Yeah? So gg of x you define as 2x. Now if you get gg3, yeah, you get 6x. You get 6. Yeah? So now how you can use this, for example, here down here is again the Fibonacci with the function overloading. Yeah? So I define Fibo of n, where n is a pattern. So I can now replace, so whatever comes, not whatever comes, but when something comes that is not defined like this, it will replace it by Fibo n minus 1 and Fibo n minus 2, right? And then I also define Fibo of 1 and Fibo of 0 without pattern. So if Fibo comes with 1, so you see, I don't need to have an if statement. Yeah? I just define the function whenever Fibo comes with 1. Then this is 1. When Fibo comes with 0, this is 0.
Here I have a question, because we had before the lazy evaluation for ODEs, which were two equal signs, and here we have a lazy. Or these two equal signs are just for equations?
So the lazy is a comparison. It's an equal sign. Mm-hmm. Column equal sign is a declaration. Okay. Yeah? Okay. And it's a lazy declaration, whereas the single equal sign is an eager declaration. Okay. Which I believe is exactly what we talk about here. So the solution is already on the slide. Maybe you don't read all of this. No, this is how you don't get. So this is very difficult. So I have to watch your eyes. I mean, okay. So doesn't matter. You can read it. So let's say we define in an eager assignment x equals to 3, right? And then we try to compare this, say this is 2x eager, so we've defined 2 times x as an eager assignment, and then we define 2x lazy as a lazy assignment. And then we do, okay, then we evaluate this. 2x eager is 6, and 2x lazy is obviously also 6. Yeah? Okay, then we do, so then we change x to 4. So what happens to 2x eager? Because we assigned this eagerly, right? It stays what it was. So because it executed, here it executed what we had here. And this 2x lazy kept the structure intact. So it actually saved the algebraic structure, yeah, and it will be 8. You have to know that if you don't use these things properly, this leads to very difficult to understand mistakes in your program. Right? Mm-hmm. So let me try to absolutely confuse you. Okay? So let's say I'm going to repeat this. Yeah? So say I make 2x eager as 2 times x, right? Mm-hmm. And then I make 2x lazy as column 2 times x. Okay? So one difference that we see is because the first one did this execution, we get an output. The second, because it's lazy, it doesn't give you an output. Okay? So, okay, what did I end? Okay, I forgot to put the x here, so that x is equal to 3, right? So, and this is an eager assignment. So then 2x eager now is 6, and 2x lazy is also 6. Okay, so this is now we are here. We repeated this. Let me see whether if we put x equal to 4 and we still have 2x lazy, or I'm just using the other way around. Okay, doesn't matter. Let's say 2x eager. So what's the result?
It should be, or I think that it would be the first spiral, which is 6.
So you think it's 6?
Yes. Okay.
So what's the difference?
Comparing both, maybe the well, no, this is used to change length, right? Or to tell the cell that you're writing another expression. Or in your perspective would be like this.
So you think I'm missing the column? What is this? The semicolon.
Mm-hmm. Yes.
So okay, I did not talk about the semicolon. The semicolon is suppressing the output.
Okay.
Yeah.
Or maybe takes the last. It could be eager, but takes the higher variable. It goes back to the cells, or the cells are independent.
No, it's not. The cells are independent. It is not going. The cells are all independent.
Okay.
So there is, okay, I tell you something else, okay? So maybe sometimes you just have to restart. So what you can always do is you can go evaluate notebooks, so it will evaluate everything new, right? So let's do it anew, and now you are right. I mean,
but why?
that seems to be even more confusing, isn't it? So what was the difference before? You know,
I understand that you forgot to.
Yes, I did this here later. I put x equals to 3 later. So when I asked Mathematica to eagerly execute 2 times x, it was not able to execute this because x was not defined. So there was nothing else it could do other than storing it lazy.
So would that mean that if you did that again, for example,
so no,
the first case was eager.
Now since I now defined x, yeah, so this will now always be executed eager.
Okay, so what I'm trying, or my question is, the first case you forgot the x equal to 3, so
yeah.
you define eager to x. So
I didn't define 2x eager. So 2x eagerly defined is 2 times x, but it cannot simplify 2 times x.
Yes.
So it would actually execute 2 times x, but executing 2 times x gives 2 times x.
Yes.
Yeah?
But does that mean that you had 2 evaluations when you forgot? The first one was, we saw that it was 6, right?
Yeah.
If you do that again, for example, changing x equals to 5, will it change again, or it will remain as 6?
Then it will remain as 6.
Okay.
No, wait, no, wait. Before I define, sorry, not like this. If it's once the set, okay, yes, now I understand your question. This is very specific. Yeah, no, it will. I mean, because it was assigned 2x, yeah, it will remain 2x until you assign it again.
Oh, okay.
Yeah. Now since I assigned it again because I ran the notebook again, yeah. Now it's changed to being actually the value 6, because when I did it again, it could execute this.
Okay, so in the first case, it would be
like it would behave like a lazy,
okay.
Yeah. It would behave lazy. Okay. So there's another. Yes, so it will store it like this. So there's another thing that is potentially not. I mean, just for understanding how Mathematica works, it's important. Maybe you should not use this. I mean, this is not a good way of programming. Yeah. I mean, don't do this at home. Yeah. Just for the understanding. So Mathematica is storing actually everything in a kind of list type format. So as a this list is something different from an array. So because arrays always have the same size, so it's like you have a follower. Yeah. So the way a list in Mathematica is declared is by making these brackets here, and so you put these entrances, and then then there is each programmer will always ask, is this Fortran style or is this C style? And then because languages are to be distinguished between C and Fortran style, meaning they count from 0 or they count from 1. C counts from 0 and Fortran counts from 1. And then you say, I mean, yes, this is a little bit like what does yes and no mean in Chinese, and then they will say that one is shi and the other is bu shi, yeah. But actually, this is both. This is not really yes or no, because the language doesn't have a yes or no. They have it is like this or it's not like this, yeah. So I mean, the concept is a bit different here. It's not that it just starts at 1. Actually, the list starts at 0, but it comes with a header. So the 0 element does not contain any elements of the list. The 0 element contains the header saying this object that now follows, so all of this is of that type, right? So the first element, so we do a tracing by taking this, these two brackets here. So this gives us the first element, but it also has a 0 element, and this is just saying that it is a list, yeah. And now you can actually do very crazy stuff with this. For example, you can put the 0 element to something else. Say you put the 0 element of this list to plus. Yeah? So what you get 10. Why? Because 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. You replace this. You say this object is not a list, but is a sum of this whatever follows, and this then gives you 10. Yeah. Okay. So you can do stupid stuff here. Yeah. So you can define magic A plus B. So this has a 0 element that is plus. And then you can put magic 0 2 times, and then you have it A times B. I mean, this is why I say don't do this at home. Don't try to program like this. Just get an understanding how Mathematica is dealing with these types. Okay, I kind of believe I'm coming to the end. Let me see, is there, yes. Okay, so there's anyways in German. I told you these are old slides, so you probably don't get a CD. I mean, Mathematica does not fit on a CD. By the way, if you have to download it, it's a bit a bigger thing. But what you can do inside this campus is you go to the so forget what is on the stupid slide. Yeah. So you go to the Gauss IT Center website and look for software, and then you can they would give you a link where you can download Mathematica, and then there would be instructions that may be different from the one that I have here on my 10-year-old slide. What license server you have to use. Yeah, so because I'm not making any advertisement, yeah, and the stuff is also expensive, as I told you. So you can use some licenses from, so some campus licenses, as long as you are inside the university network. So you may need to have VPN on, yes. So, and I mean, in principle, we can use these computers here to use Mathematica, but you can also download it on your own computer. Maybe this is more convenient for you. Due to the fact that I have another lecture just following this, I prefer to be in this room, yeah. Yes. So, then how to learn Mathematica? I mean, you come to this lecture, but I'm not telling you everything. We also, this lecture will introduce also a little bit more mathematics that is a little bit further away from Mathematica. I mean, the lecture in itself, I'm not going through all what Mathematica can do, especially nowadays, since they are running out of new things that they can. There's computational geography stuff and everything, and of course there's a lot of machine learning. I mean, if you are very interested in anything of these, we can maybe attend this. So my idea was here to talk more about solving differential equations and how to set up differential equations in a way that they can be easily solved with a computer algebra system. Yeah. So then we'll have more. We'll have a little bit of physics and mathematics in here, where we, understand the part that the human has to do, and leave the other thing to Mathematica. So then, when you still, of course, so if you still want to learn Mathematica, then actually Mathematica has, or I would rather say, unfortunately had, in previous versions, a pretty good helping system. Yeah? So, online help. So, in previous versions, let me see, we have 2 minutes. I guess, so there is help, yeah? I had a little bit the impression that this did not improve really with time, the help system. So let me see. Let's say we want to do plotting, yeah. Okay, so this is stupid. So previously, what it previously did, you get more or less the same results as this. Okay, I'm even using an old version of Mathematica, but never mind. Yeah. So, okay, there's no help telling you what was better in the past, but in the past, the Mathematica help would open in Mathematica. So what you were able to do is you would be able to go here, modify this and execute this. So the way you are now supposed to do it is because they send you online. Yeah, so they comes online. Now you can copy this. You can put this. So this previously this was automatic. Not even that worked. As I told you, this used to be better. Direct link to example. Okay, I'm sorry. Yes, so there's no, okay, I cannot execute this again. I guess you can somehow copy to clipboard. these things just get, so you can copy it, yeah, and then you can of course kind of modify this. Yeah, but anyway, so they usually have a relatively good explanations for example, what options you can use. They give you some applications. They also give you neat examples. Yeah. So eigenfunction of potential well, yeah, looks pretty. So this is what I call, and here you get the links to see also, I think. So the log plot, yeah. It was better when it was built in. Here's also some details on this. So this is, don't look for any other literature. I mean, as long as we talk about Mathematica, of course, yeah. So they explain everything in here, and this is also the way I learned this. Yeah. So you go really to the help, and yeah. Use this here. Let me see. I'm kind of believing we have come to the end of this. Yes. Okay, we also come to the end of the time. Let me see whether I can stop